Hey everybody, today we're going to actually start to prove some conditional statements like more formally. And you could always use something called just direct proof, which would just be to assume the P and show Q. But like we've been talking about for the past few days, like there's sometimes cases where something like a contradiction, which we won't quite talk about yet today, or a positive might work better. And so contradiction, I haven't really written it down yet, but basically we're just going to be assuming not Q, and we're going to show some sort of contradiction arises. For contrapositive, we did some of that before. We assumed not Q, and we showed not P. And that's kind of the big three. There are technically other ways that we will prove things, but they're mostly just like variations actually on these three kind of. And I thought this was funny because this is, I honestly thought about now more as like a teacher, because so much of what I teach really fits into more engineering. And I always kind of, as a teacher, I'm just like, why? I get kind of bummed out that students don't always ask the why question. And mathematicians, we love to know like why things work. And if you don't know this guy, he's really funny, and I think you should go check him out. But this guy is someone named Zach Starr, and he actually has like really good videos on a whole bunch of like math and engineering. I think he was in a PhD program in engineering, but he also has some funny videos, and they're like things like this where it's like mathematicians sitting in engineering classes, and we always want to be doing proofs. And we want to know, like, why does something work? And so oftentimes in math classes, like, we've had a lot of students go onto Minds and things like that. Those kind of schools, they're not always super concerned with why something might work. They just need to know, like, how it works. And then they implement it in, different ways to utilize the fact that how has already been shown. So math people are sort of the first ones to kind of tackle a problem, the big problems, and then engineers and physicists and stuff take over. But this is very much how I felt in a lot of my classes. I was always just kind of wondering why people didn't want to ask the big questions. And for like the next few days here, we're going to kind of actually just ask the big questions and really like show some ways to answer them, basically. So the simplest one is direct proof. And direct proof, like literally, we're just going to assume that P holds. Like we assume this statement, and we're going to use that to show, something over here, Q. So in this example, like if X is odd, we could just say if X is odd, then, by definition, we know that X equals 2n plus 1 for like n in, I was about to write the reals, but in the integers. And then if we do, we could just say something like, so x squared equals 2n plus 1 squared, which is 4n squared plus 4n plus 1. And then what we really want to do is we want this to look like 2 times something plus 1, so that we can conclude, so x squared is also odd, basically. And the way to just do that is to, factor here. So if we take a 2 out of the first part, we get n squared plus, nope, that's not what we get. We get 2n squared plus 2n, and then we get a plus 1. So that equals 2 times, actually I'm going to kind of give myself a little more room here. Equals this, we're going to say period. And I might just add note 2n squared plus 2n is part of z for basically just the reasons that multiplication of integers is still an integer, which you don't really need to say. You can just say like, note blah, blah, blah is in Z, so x squared is also odd. But that's like just a simple direct proof. It's almost so simple. Sometimes it's hard to prove the simple ones, but you just assume that P is true, and you're going to use that to show Q is true. That's the simplest kind of proof, and if you can do it, you always should do the proofs that way. In linear algebra, it's definitely going to be a lot where we can't just assume P and show Q, but that is always the easiest way if you can do it. So I just want to do one more example, and it's pretty simple. Just if A divides B and B divides C, then showing that A divides C. One thing too, it's always good to sort of get an understanding of what the proof or the proposition is saying. So if you just think like, picking some numbers like, I don't know, 4 divides 16 and 16 divides 32, so 4 should divide 32. Doing these kind of things, just thinking about that in like your head, can really help like make sense of whatever we're doing, especially when we start applying these to like real linear algebra, like much more challenging kind of problems. So this one, again, you can just do direct. So we could say, if A divides B, then by definition, we have that B equals A times, N for N in Z. Also, B divides C implies that C equals B times, I just need another letter, M for M in Z. Then, if we just do substitution, so we've got B, and we got B here. So if we basically sub in, so therefore, C will equal ANM, right? And basically, if we just group those two, we could add like a, note NM is in Z. So by definition, right, we know that A divides C. So that's just like a super, straightforward, again, direct proof. Just assuming that this part holds and using it to show this part. That's the idea. So one other technique, it's still direct, which is why I want to talk about it here, but it's kind of like a variation on a direct technique, is something called proof by cases. So cases, basically what it sounds like, you're still working with the P, the starting kind of, assumption over here. You're still going to show this, but the way you do it is kind of different. So we're going to basically take a proposition and split it up into cases. And sometimes the cases are kind of confusing. This is kind of the classic case breakdown, like x being less than 0, x equals 0, and x being greater than 0. There's this thing called the Triangle Inequality, which I realize over here you can't quite see it, but you can do this with vectors. It's kind of the easiest way to talk about it, but you could also talk about it with just even sides of a triangle and just use like absolute value. But so assume these are all vectors in here. So this is something called the Triangle Inequality. And the triangle inequality really is just easiest to show in a picture. Like if you've got vector x, and then you've got vector y, then this vector right here, right, is x plus y, right? And if you just think about it, that blue vector has to be shorter than going up and then down to the same spot, right? This is just the hypotenuse of that triangle, but this hypotenuse will always be less than or equal to this because you're going to go up and down and still end up in the same spot. So you're going to have moved a bigger distance than just moving straight across that hypotenuse there. But the way you actually prove the triangle inequality with like vectors is doing proof by cases. So you assume this is probably pretty small to see, and I'm going to show you another example, but you can assume that x is bigger than or equal to 0 and y is bigger than or equal to 0, and you can work through why that would lead you to this inequality. Then you could assume that it is specifically less than 0 for both of them. So this is kind of your positive and 0, this is your less than 0. And then another case would be just their alternate. So maybe like x is positive and y is negative. And they do this classic trick where they say, without loss of generality, assume that one is positive and the other is negative. So if you could just sort of assume that without losing any of the proof, because x could be y and y could be x. So there's nothing wrong with just like proving this as one case and not having to split it into two more, like into another case. But this is just like a famous problem that uses proof by cases. There's one in the book that I think is kind of good to go through. So it's kind of just a weird number theory question again, but it says every multiple of 4 equals 1 plus negative 1 to the n times 2n minus 1 for some natural number. And this is done with proof by cases in the book, and it's probably the easiest, most like direct way. So I'm going to, if we take this, so like I'm going to say let 4 equal, actually I'm going to erase that. So I'm going to let 4 times like a equal, I don't know, k. So this is basically my multiples. So like 4 times something equals k, and that's like what it means to be a multiple, right? And I need to show that this equals, so that 4a equals k, so I'm going to say we will show that k equals 1 plus negative 1 times n to n minus 1 for some n. That's the idea. So case 1. I'm just going to let a be 0. And a lot of times when you do cases, you can just sort of do this where you put in parentheses next to like you literally do write the case out, but then you could just put in parentheses a equals 0 case. And to do this, you really just need to find like a way to make this work. And the simplest one here would just be to let, if you let a equals 0, you could just say like something like note n equals 1 works, and then just show it. So do like 1 plus negative 1 to the 1, and then 2 times 1 minus 1. All my parentheses are good there. So what's going to happen here is you're going to get 1, and then you're going to get minus 2 minus 1, right? And so you get 1 minus 1, which is 0, which equals 4 times 0, right? And so that would prove the first case, because you just need it to work for some n, and that does it as long as you find one, like the number 1 there. So another case, we'll do just different color. Case 2, I'm going to do the kind of classic, split the a up into different parts, the equals 0, greater than 0, and less than 0. So here, if we let n equals 2a, that's going to still be a natural number, because that's a messy natural number. So just 2 times like a is going to be a natural number just because it's multiplying two natural numbers together. And if you just note, so we're going to let n equals 2a, which is part of the naturals. And if you just plug everything in, so I'm going to put in 2a up here. Oh, wait, not 2a. I'm going to put in n up there, sorry. I want to just keep it the same as what I wrote above there. So we could simplify this a little bit because we know n is an even number. So this -1 could just become +1. And then we have, 1 plus -1 here eventually, so that's going to cancel. So really this is just 2n. But then n, now I think I'll plug it in. We get 2a, which equals 4 times a, which is the k that I wanted to show. So now that case is done. And then the last case, just a less than 0. And a lot of times these things you just sort of have to play around with. And, when I did this, I just sort of tried a few things, and eventually I found that if you just let n equals 1 minus 2a, that's still going to be a natural number, like n is natural. And if you go and plug it in, just say something like note, 1 plus -1 to the n, 2n minus 1. So now the -1 to the n is, so it's odd, so you're going to get a negative number there. So you're going to get 1 minus 2n minus 1. And then that would simplify to just 1, so it'd be 1 minus 2n plus 1. So then, you're going to get minus 2n, and I'm running out of room, which equals -2 times 1 minus 2a if I just substitute in, which you get -2 plus 4a. And I think I did something wrong. So I'm going to find my mistake because this should just be 4a. Okay, I paused the video and I found my mistake. So pretty sure 1 plus 1 is not 0. I'm pretty sure. So let me fix that. Okay, so we get a 2 there. And then we'll get -2 times 1 minus 2a plus 2. And now we will get to -2 minus 4a plus 2, or plus, 4a, and then those cancel, and that is k. Okay, I ran out of room, but every time we can show that some n will give me 4a, or some multiple, of 4. That's what the k is, right? It's just a multiple of 4. So that's just another example kind of using proof by cases.